machine learning is a branch of data science and artificial intelligence that teaches basically you teach your computer what to do, how to understand patterns, and not just like it's different from traditional programming I mentioned, where you use programs like you're telling your computer, this is what I want you to do. In like for example, you can tell your program, okay, I want to write a program that my function is +2. So whatever I'm given, add two to it, and that's what you do when you start um, writing functions in Python. You tell your function that this is what I want you to do. So, but in the reverse is the case when it comes to model training, machine learning. You let the model or the machine learn from itself. So you give it maybe a problem and the solution or the desired outcome. The machine looks at it and looks for patterns in the data and kind of suggests a function that best suits the input data you've given it. In during this process, it's called fitting the model. So you're fitting the model. So that in machine learning, there are some machine learning algorithm also generally for different things. Then you want to fit it to your model. So you're able to your data rather. You want to fit that model to your data to produce something that you can use. And this process is called fitting the model. You're training the model to understand data. Then subsequently the model which you've produced from your process of training is like teaching a child how to identify something, like teaching a child A, this is B, so that tomorrow the child can understand that this is A, or this is a cat, this is a dog, this is a man, this is a woman. So subsequently, the model which produces from training the model cannot be used for future predictions. So that's where you do model the prediction, making predictions. So when we go into the live session, you understand how this works, how you fit and train model, what that means. Well, this is the science behind machine learning. So you're not giving the machine the answer, you're just giving it data, and it learns from the data and comes up with possible answers. Then as humans, that's when we evaluate the model to see this answer this machine gave me. Is it good? Is it good enough? Or can it be improved? So these are some conversation we start having when we start talking about hyperparameter tuning, model tuning. So there are different types of machine learning. We have basically you have three types. Some people tell you for when you talk about semi-supervised learning. So we have supervised learning. What does this mean? It means you kind of teaching the model based on outcome. So you say this is the you have label data. So when you talk about machine learning, you have labeling. So that's more like this is a cat. Give it properties of a cat and say, okay, this is a cat. This is give different properties of a dog and say this is a dog. So the label, the dog associated with that attribute is the label. This drug associated with that cat is the label. So you are more like, okay, this is a cat. Whenever you see similar thing, know that it's a cat. And one thing about supervised learning or machine learning in general is the data set you're using for training should be similar, should have the same similar attributes. More like if you're giving you train your model with 12 columns, if the model needs to predict, it needs to make prediction based on those 12 columns also. So the model, the subsequent output input you want to give it to maybe predict based on the model should have a similar structure. Yeah, that's so supervised. You have a labeled data set, but unsupervised, you don't have any labeled data set. So the model just simply goes through, looks for patterns. For example, um, you could have like I said, like use my cat and dog example, where you have different cats. You say this is a cat, this is a dog, this is a whatever animal you want to give it. But with unsupervised, you're not telling this is a cat, this is a dog. You just give it everything, and based on the model, kind of group things together to find pattern. It's okay. The model can say, oh, all these animals they have whiskers, so let me group them together as one. Then you'll be the one to go and say, okay, this group that the model has given as one, maybe this is a cat, so you'll be the one to assign something to the cluster or the group that the unsupervised has given you. So it's more like looking for what is similar among those things and kind of group similar things together, and on similar things group them separately. So there's no predefined target. there is no label assigned to it. On the other hand, we also have reinforcement learning. This is more like the model learning from his own mistakes. So it's like teaching a child to how to stand. The child will try to stand and it falls down. You don't beat up the child. The child learns tomorrow, okay, this is how, if I want to take a step, this is how I do. So that's how you think about machine learning. Sometimes you train the model, it improves on itself. So whereby you favor, so it's more like trying different trial and error method to see which works. So the ones that the time it gets it right, you encourage it or you reinforce the model. You are reinforcing favorable outcomes and discouraging unfavorable outcomes. That way, the child or the machine learns from itself. Okay, if I've been punished for this or I've been discouraged about this, maybe I wouldn't make this mistake again. And when I'm being praised, if okay, this thing is good, so I should continue doing it. So that has what reinforcement learning is all about. But for now, we just pack supervised learning and reinforcement learning later on. Like we're not going to treat it today because it's very complex and it's as basic as you can be. You start with supervised learning and this from there you can build on to other things. So there are two main types of supervised learning. We have classification where you're predicting a category, such as maybe, like I said, predicting is this a dog or this is a cat? Is this email a spam or not spam? Just predicting when you talk about classes, that's what you talk about classification. Why regression is you're predicting a continuous or numeric variable. Someone like you can predict, let's say the price of a house or stock prices or just anything you think about numbers, continuous numbers, or maybe this test score we're trying to do the last week. Those are regression problems. So we can put this into perspective. Let's say I want to predict whether tomorrow's weather will be hot or cold. So within you have your temperature gradient or temperature, different temperature. You have been able to establish, okay, anything below 60 degrees is cold, anything above 60 is hot. So you can now put this as a classification problem. It's okay, I have my input data. I want to predict if it's hot or cold. But in the same kind of data set, you want to predict the exact temperature. That's regression. So, like everything we're going to do is about temperature. Like for this example, it's temperature, but the approach differs. If I want to make it a classification problem, I can just group it into maybe 2 or 3 classes depending on you. So, I want to predict class 1, 2, or 3. Or if I want to make it, I want to be exact, then I'll go through a regression problem. So classification is when you are trying to predict a class. So if I want to predict if this is black or white, I want to predict if this is a cat or a dog. If I want to predict if it will be hot or cold tomorrow, it's classification that you are predicting class, not a number. But if you're going to predict numbers, exact numbers like, oh, what's this person's tech score? What's the price of this house? You want to train a model to see what the price of a house will cost based on different features, or the price of a car, or let's in this case temperature. So we are predicting the exact number. Is regression. So when you talk about numbers, continuous variable is numbers. You are using regression. But if you are trying to group them, class A, class B, this or this, for example, if you are a geoscientist, you want to predict if something is shale, a sand or shale, you want to talk about classification. You want to maybe predict or if you want to predict porosity of your reservoir. So when you train machine learning models, so if you are going for a classifier, so if it's a classification problem or regression problem, there are different models you can use. So this just shows the different models that can be used. So for example, I have my data set now. It's a classification problem I want to solve. There are different options I can choose. You can go for linear models using logistic regression, or you can go for tree method using decision tree classifier. On the other hand, you are doing a regression problem, you want to look at linear method or linear model, you want to look at linear regression, lasso. So these are different algorithms that you can see. So as we go into the session, you understand how to use this. And when we talk about linear regression, logistic regression, random forest. So for the ensemble, for example, you have random forest regressor, you also have random forest classifier. So they have their best. So if you're trying to use classifier for a regressor problem, you might not get the right result you're looking for. So you just understand that, okay, first of all, you want to know, am I going for a classification problem or am I going for a regression problem? Then you now ask, okay, which model do I use? So you follow that tree like that. So now just talk about workflow generally, like data analysis, data science workflow. You first get your you want to ask yourself, what's the problem I want to solve? Let's say you're in an organization, they want you to do a project. The first question is, what problem do I need to solve? Then you now go, what data is available? What kind of data do I have to solve this problem? And if you're working in an industry, so sometimes depending on the company structure, some of the tools you use to check your data or for data management or retrieve data, you have SQL, you have MySQL, some database like Oracle, Postgres. Those are like involved. So if you want to deal with data itself in itself, because there's a field called data engineering. Those are the people that handles data management. So these are the tools they need. Then you're not going what's contained in the data. So for example, now I understand the problem I want to solve. I understand the data I want and I've retrieved my data. Then I want to see what is in the data. What can be contained? What are the things I can do? Just understanding your data. That's where data analysis comes in. Understanding the data, and there are different tools you want to use for data. That you have your pandas, you have NumPy, you have Matplotlib. Those three libraries make up the Python data analysis ecosystem. You have Seaborn. Those are the things you use to analyze your data. On the other hand, some people for data analysis, some people there are other tools you can use. There's people use Excel, some people use Power BI, some people use Tableau. It just depends on what, for example, whatever works for you, whatever you understand better, and what your organizations. There's some companies that use Power BI, other companies use Tableau, other companies use Excel. Just understanding that, but the concept about data analysis is the same, irrespective of the tool you're using. That's why I push for people to understand the science, not the tool in itself. Then you now go into data transformation and transform your data. So based on your EDA, you understand, okay, what are the things I need to be transformed in my data? Then that's when you start going into model training. But this is more data science related things. And most times this process is iterative. You go all the way to model training, find out that, okay, we need to adjust this problem I need to solve because the data I have is not available. It's not enough to make this decision I want. You can go back and go through that loop several times. Sometimes it's an iterative process. So now let's just go over to data transformation for the purpose of machine learning. So we've done a lot of talked about different data transformation, cleaning your data, making it uniform, normalize your data, all that. So if you want to now transform your data for a machine learning problem, you want to you want to start you want to go through preparing your data, and preparing your data encapsulate different things. Talk about data encoding. Most times when training models understand numbers, so you need to transform those categorical values into numbers. That's when you talk about data encoding or decoding. If you're going the reverse, then you normalize the data, so ensure that they are all within the same scale. Then you split your data. Training data, when training a model, you have the test data and you have the training data and the test data. In some cases, also validation data. So you should be split. So as part of transformation for machine learning, you want to split your data into training and test set. You train the model on the training set and test the model on the test set, or evaluate your model on the test set. And most times when you train your data, you split your data into X and Y. So for your train data, you have your X train and Y train. So the Y train is the predictions or the labels you have assigned to the data. YX is the features. So you split your training data into X train and Y train, and you test data into X and Y also. So you have your X test and Y test. You understand what this means as we go on. So for your training data, so when training the model, remember when the first slide, you put your X train and your Y train into the model, it brings out results. Then for your test data, you put it into the data to make its own prediction. When we get into evaluation, I will explain what that means shortly. Okay, so no. Okay, so then we go into model training. So there's also a workflow from where you want to train your model. So after you, let's say you predicted, you transformed your data. The data is now machine learning worthy, because most of the time the main work is in transforming and cleaning that data to fit into the model, because the quality of your data determines the quality of the model. If you have a bad data, rest assured that your model would not be accurate. So first of all, you want to choose the model, like I said. So there's this clean sheet, scikit-learn. Scikit-learn is a library in Python that, at least as beginners, as you want to use it, it has everything you need to know or you need to train a model efficiently. So first of all, you want to let's say go into this clean sheet. So for example, you start from it. This is just like more like a dummy process you can follow as these beginners to understand if you're not sure of what I want to do. You start. Do you have to also you need good number of samples to carry out machine learning model, machine learning problem or algorithm. So you first feed in, look at your model. Do you have more than 50 samples? If no, you just go get more data. If yes, you continue the journey like that. Predict the category. So you want to understand, is it a classification problem or a, so I want to predict, is it a category? If yes, if it's a category, you move over here. If it's not a category, if it's maybe like a number, you come over here. Then you follow. So this part just takes you over to regression. So this is more for regression. Then if it's labeled, to ask you, do you have a label data? If yes, you move over to classification and yeah, go through. If you don't have label, you want to go into unsupervised as clustering. So I don't really have labels, but I just want to understand my data. I want to see if model can predict any patterns in the data. You move over here to say cluster things together. Then you just go there and there are different models. So I think at this point you want to start working like explain if you have over 100k samples, you want to try linear models. If it's not working, you want to try different models. Most of the time it's more trying different models to see what works for you and what you can use going forward. Yeah. Okay. So now the next thing, you want to fit your model. You see how you fit your model. When you are choosing the model, you want to fit the model. Then you want to start making prediction using your predict model, the predict function or method. Then you want to evaluate your model. So remember when I talked about you train the model, then after training the model, you want to understand, you want to evaluate, you want to score your model to see how well my model is doing. This is where you start evaluating. So depending on if it's a classification problem or a regression problem, there are different evaluation you do for both of them. Different. So if I'm doing solving the classification problem, I want to focus on accuracy score, F1 score, precision score. You understand all these different score or recall. Then if you're looking at regression, you want to look at the mean absolute error or the mean square error or R square. So these are, maybe when we get there, we'll explain what these different errors means and how they affect your model. So remember when I talk about you make your prediction, then you compare your prediction with your Y test. So that's the actual value. Remember, you split your data into test and training sets. So you predict using the X test, then the prediction, then you compare it with the Y test to see how, because this is the Y test. Because the Y test is the actual true value, but the prediction is the what the model predicted. So you don't want to be so far from the actual. So that's why you're comparing. So the models that is closer to the actual number or the actual test, that's the model that is more accurate. Another thing again, going from there, we want to talk about improving model. Okay, so let's do this. So you want to after yes, you want to also, if for example you train your model and your model isn't doing so well, you want to improve the model. That's where hyperparameter tuning comes in. That's where hyperparameter tuning comes in. It's like adjusting different parameters in your model so that it fits your data properly. While doing this, you want to be wary of overfitting your model, because overfitting, if you let me go there, we'll go back to talk about overfitting shortly. Yeah, we'll talk about overfitting shortly. So after improving your model, you save and load your model. then deploy. So let's talk about overfitting model. So when you overfit your model, an overfitted model is a model that performs very well on your training data. That means it captures all the noise in your data and it fails to generalize on other data. So it works very well on, so for example, if you evaluate your model on your training data, you get 100%. Well, when you bring a new data that the model has not seen, it doesn't do well in it. That model, call it, it's been overfitted to the data, and that's not good. You want a model that can make generalization, that can be generalized. Why an underfitted model is a model that does not even perform well on your training data. So if it doesn't perform well on your training data, how would it perform well on test data? So it fails to underline the trend. The major thing about a model is to pick the general trend in the model, not to just pick every point, but understand the patterns. So it's about understanding patterns. So if you look at this first model you're underfitted, you see that this is the pattern of the data. The model just went to pick on this one. So this model would perform very poorly, it's underfitted. This model on overfitting is picking out. So all this wiggle pattern is not really the pattern in the data. Some of them could be noise. So the model is picking out the noise. And if you put this model into another data, how well would it capture all this noise? It's going to be difficult. So it's going to perform poorly on the data set that you have not seen at all. But a balanced model is a model that is not 100% accurate, but you see that it can capture most, like it captures the pattern very well in the data. It captures a trend in the data.